All right, well, thanks everyone for coming out to this amazing talk. As you will notice, Jason is not up here with me, and he will not be appearing. In all seriousness, he was recently in the hospital, so he's at home recovering. So he's very sad that he's not here, but I will do my best to give this presentation without him. So if it's a train wreck, blame him. If it's awesome, it's all me. So actually, this is our fourth year here, and real quickly, was anyone here, or have you at least seen the talk that we gave last year? Show of hands, anyone? All right, cool. Well, in case you missed it, which is apparently everyone, we'll recap that a little bit here in a second. So who am I? Well, I am currently the CEO of a company called Nexosis, and that has kind of a cool story. Last year when we were presenting here, the video that was recorded, some people saw the video, and we went and talked to them, and then basically as a result of that, Nexosis was formed. So, companies are formed at DerbyCon. That is the moral of this story. I used to be a penetration tester / researcher for Hewlett-Packard, and beyond that, I used to work for American Electric Power, the Ohio Department of Taxation, a bunch of other fun places. Not really. They all kind of suck your soul away slowly, but it's a different talk. So yeah, this is actually kind of research that has been going on for about 3 years. We'll go back to 2013. Jason and I started this video game company called White Wizard Studios. And we were a little bit naive to think that you could make a video game on like $10,000, but we tried it anyway. And we were actually going to make this game, like it was going to be pretty cool. It was going to be like this isometric thing, and we were going to have this information security / cyberpunk feel to it. But one day we were just kind of thinking about the gaming industry and all the problems that it has. And one of the problems that it really has is cheating in online games. And I'm like, well, that's something we should look more into that. Like, how would you go about solving cheating in online video games? Because as you start researching this, you see the traditional method is really signature-based stuff. If you start looking at the end-user license agreements that companies like Blizzard and Valve and Activision, they all have you sign, they're basically allowed to monitor anything you do on your computer. So they are allowed to look at your tabs that are open. Valve was called out recently, well, this is 2014, for looking at your DNS cache. Like some pretty invasive stuff that really people don't know what they're doing. And Gabe replied on Reddit, he said, look, you guys just got to trust us, okay? We're not doing anything malicious with what we're gathering. We're just trying to stop cheaters. That really didn't go over that well with a lot of people in the security community, but regardless, I mean, this is still how they're operating today. So our theory was back then, well, what if you use machine learning to look at player behavior? Because at the most basic element of what a cheater is trying to do is he's trying to give himself an unfair advantage. So we're like, well, if we start looking at all the statistics that are with cheaters, you might be able to use machine learning to find out, well, hey, is this guy cheating or is he not cheating? So that was basically our operating theory on that. I'll go over real quickly kind of what the results were in the next slides, but it's pretty good at doing it. And then that brings us today. So now we have Nexosis. Basically what we're trying to do is build a machine learning platform. So what that means is we are trying to make it easier for people to create applications with machine learning. So the goal of this talk today is really to get you all to start thinking more about machine learning. It is definitely coming. It is coming very quickly. There are lots of new players in the market every year. Lots of grandiose ideas of how machine learning is going to be this magical silver bullet. I will tell you, it is not a silver bullet by any means. It is very, very complicated. And as we go through the talk, you'll see why there will never be a product that can just say we use machine learning and now you're going to be safe. So there is one slide on here that has some math on it, but I promise it's very fun math. So real quick overview of the anti-cheat, because I do think that it translates well to what we're trying to do with information security, whether it's finding SQL injection attacks or anything similar. What we did was we used something called supervised learning. So all that really means is that you have a data set that contains the information that you're looking for. So in our case, we had a data set that had a bunch of cheaters in it. I think initially we had something like 120,000 records of here's what these cheating stats look like. And then we went and we found all these professional players, and we used those as our legitimate players. So there's some issues with that approach, but it was honestly the best approach that we could have. We ended up having to use like the Steam API, which has injection issues, so people could just falsify data. There were all kinds of hurdles and obstacles that we had to overcome. The end result was back then, so in 2014, we were about 83% accurate with the machine learning models that we built. And essentially what someone could do, I mean, this is a fully working proof of concept. We have this website up, you go there, you type in a Steam ID, and it will basically tell you whether or not we think they're cheating. And then it has a score associated with it. So here's an example of someone that we suspected of cheating. Down below, it would show all the metrics and what we thought were important, what we didn't think were important. And here's Jason's account. So Jason does not cheat, is basically, well, that's also true, but the machine learning system said he also doesn't cheat. But something really interesting happened about 6 months after we gave our talk last year. We posted on Reddit, and a lot of people upvoted it, made it to the front page of the Counter-Strike Global Offensive Reddit page or subreddit page. And as we were monitoring it, we looked at the cheaters and what they did. And one of the features that we use in our models was accuracy. Like, if you're using a cheat to increase your accuracy, you would assume that your cheating accuracy would go up. And you would see that in the data. So the cheaters, honest to God, they changed their cheat system and they built in an accuracy slider. So you could actually tell the cheat like how accurate you wanted to be. So that was interesting. There are a couple of case studies that we wrote about it. Here are the links to them. There's an actual link to our site where you can download the full case study. We go over the entire process, including the feature engineering that we did and basically how we got it from 83% up to 93%. So we had some pretty good improvements. But now moving on to Infosec and all the fun stuff that really relates directly to you guys. I thought we would start off by doing a little bit of an experiment. So is anyone here on what I will call a blue team or an incident response team? Raise your hand. Okay, this is great. So you people who just raised your hand, I have a question for you. I have no idea what organization you work for, but how many of you guys think that you could detect a breach in under an hour? Show of hands. Okay. I do not see any hands. How about under 24 hours? So I think we have 3 people who raised their hands for under 24 hours. How about under a week? Okay. I think, was anyone not under a week? All right. So we'll go with everyone here who is on a blue team incident response says under a week. I'll show you the results that we got here in a second. So remember that. Everyone here said under a week. But it's really interesting, too, because we keep hearing about all these data breaches. And when I was at HP, I worked a little bit with their DIS unit, which was their incident response unit. And more times than not, we would see breaches that took place like 200 plus days ago, and then they just now discovered it. So long time from the first incident or the first indicator of the compromise to when they actually detected it, long time takes place. And I think what we kind of commonly hear in the industry is, well, you know, we get breached a lot because it's the users, right? Like the users have weak passwords, the users go to silly websites, the users are just, you know, they're a problem, they're a thorn in our side, right? And I know at a previous company, one of their big initiatives was, well, we need to make the users on our team, right? Like we need to harness them and they need to tell us stuff when it happens, and it didn't work out very well. So, you know, we keep doing the security training, keep trying to make the users part of our overall defense mechanism. It has mixed results. So going back to what we just did, and the survey here was everyone said underneath a week. So we did our own survey. We found a bunch of CIO, CISO levels from a bunch of different companies. Everyone in our survey had a budget of at least $20 million, okay? So fairly large size companies. And we asked them 2 questions. First question was, when it comes to prevention, how well do you think your organization would be able to prevent an attack? And then we broke it down as far as like if it was a known attack, how well do they think they could prevent that type of attack? If it was an unknown attack, i.e. like a 0-day, and then what about social engineering? So these are kind of the results. We've rated it out of a star system. So if they felt that they were, really good at detecting known attacks, which is over there, I guess that'd be your left. Most people felt pretty confident about that. And then you can kind of see, though, the trend is no one really voted under 3 stars, which, okay, that's great, but, breaches keep happening. So I don't really think, the reality of the situation, what they're saying might be a little bit, well, they're not accurate, right? So then we asked about detection. And this one was kind of really surprising to us. We said, all right, so how long do you think it would take for your company to realize that you've been breached? And as you can see, almost everyone that we talked to said under 24 hours. Under 24 hours, they thought they would know that they've been breached or not. I mean, you can also see quite a few people think even like a few hours it would take them. But, I mean, speaking from personal experience, people do not know when they've been breached for weeks or months at a time. So why is that? I mean, why do we not know about the breaches that are taking place? And this really plays a big part into where machine learning fits into it, is when you look at the landscape today, everything's very dynamic, right? So you have a dynamic business processes are changing, people are coming and going. The attackers are also dynamic, right? I mean, the people who are attacking these organizations, these threat actors, are not doing the same thing year after year after year. They're evolving. And the other real problem, too, is the vendors. I don't know if anyone here went to RSA this year, but I think there were something like 500 vendors there. That's 500 different product offerings that companies are implementing into their environment. So you add all that, now add in the talent shortage, right? So no secret, information security has a huge issue when it comes to talent. The last study I read, it said something like, for every 12 jobs that are created, only 1 of them will go filled. So huge unemployment rate, we know that. Lots of work to be done, not enough people to do it. So here's the math slide. We have a lack of talent, we have a dynamic landscape, and we have way too many vendors. Basically, this results in a giant dumpster fire, especially at large organizations. Like, honestly, God, I cannot tell you how many organizations I know that have, like, 2,000-3,000 employees, and you want to know how big their security team is? 1 or 2 people. Like, okay, well, dumpster fire. That's the result of that. So let's think. That's the problem. So machine learning, again, this is where it can start coming in, how you can start using it. The first step, though, with machine learning, you have to think about your organization, you have to think about your data, and you really have to figure out what questions you want it to have answered for you. So some sample questions that I just threw up on the slide, you could start saying, well, I have all this IDS, IPS data. I want to use machine learning to look at that data set, and I don't know, maybe I just want to see anomalies in the data set, right? Things that fit outside the norm. Well, it can do that. Another kind of common example that I was just looking at the other day was malicious files, specifically Java files. So what they were doing was, it was either a malicious file or it was a non-malicious file. And they have all these different features for the two, and they're using machine learning to determine whether or not this binary file is malicious or not. But the bottom line here is, if organizations have a tool to use machine learning themselves, you start to not really care that much about scalability. And why that's important is when you look at vendors and you look at their products, they have to consider scalability, because scalability is how they make money. They can't just have 1 client. So scalability usually results in more false positives, more false negatives. So the takeaway here is your environment's very specific, it's very unique. Like I said at the beginning, I used to work for HP, I used to work for American Electric Power. Two big Fortune 500 companies, completely different in every way. Having a model that you build and try to put in place at AEP, and then you try to put in place at HP, it's just not going to be very accurate, it's not going to be very good. So when we think about traffic flow, and this is important, there's basically three types on a very high level of traffic that go in and out of your organization, right? You can have traffic that goes outside to inside, or you could have inside to outside, or you could have people talking to each other. Like, that's basically it at a high level. So if you have logging in place, what you will be able to do is start thinking about it of, well, everything is communicating over different ports, right? So if we want to find anomalies in the data set, you're probably going to do it by a port level. So if we think of like port 80, and you had all this traffic for port 80, you would make a model for port 80, and then you would find anomalies for that specific port. Now you could do it on more of a macro level, which is essentially what we did with our anti-cheat. We just threw cheaters and non-cheaters. Had we had more data and more time, what we probably would have done is made a model for every single map that game plays. We would have made a model for different skill levels, etc. And this all translates again. So you could do it by port level, you could do it by user group. There's lots of different options you have when it comes to model creation. And we'll spend more time on this in a second, but you really have to think about the question that you want answered, right? Like if it's to find anomalies, what kind of anomalies are you trying to find? If you're trying to find behavioral anomalies, that's a little bit different than trying to find like file anomalies, right? So two different things. There's both anomalies, but they're completely different. So as you might guess, though, if you're looking at all these log data and all this traffic that's coming in and out of your network, well, that's going to be a lot of data, right? I mean, we're talking terabytes of data. And this is where typically people start talking about things like Hadoop and all the NoSQL stuff. So just real quickly, I wanted to go over what Hadoop really is. So Hadoop is an ecosystem, right? It has all these different things that it can do. This diagram kind of highlights really nicely like what Hadoop does. This is HDP, which is a flavor of Hadoop, if you will. You could go out and download this today. They have a sandbox version, run it in a virtual machine, and get started playing with it. So all these things, and I don't know how well you can see it, but here's kind of the common tools, if you will. So you have Hive and HBase and all these other things, and they all do different things. Flume is important. Flume is really one of the ways, as is Kafka, to kind of get log data into Hadoop. I have an architecture slide that will kind of go over how this all works. And is anyone here familiar with OpenSock? Okay, a couple people. Are you guys using it? You are, okay. Do you like it? Excellent. Do you know how long it took you guys to set it up? Okay. So if you ever go out and look at OpenSock, the documentation is pretty scarce, and it's not an easy thing to get set up and running. It's all written in Java, that's another problem. Our personal experience with it has been that it's not very stable either. So that's our own personal experiences with it. But so if we're talking about traffic data, which we've been talking about, the basic workflow is you would have a PCAP of some form, and you would take the PCAP, and if you just want to start doing basic machine learning with it, you need to transform that PCAP into a CSV file, or an ARC, but we'll just go with CSV for now. And then there are tools out there like Weka and a bunch of other things where you could just start doing machine learning on that and finding basically the answers to your questions. So let's say that you start gathering all this PCAP data and now you transformed it into a CSV. If you remember earlier I said there's really, well, there's a couple of flavors of machine learning, but the two big ones are oh boy. Well, so you have two different flavors of machine learning, right? You either have, brain fart. Basically, you have one flavor where you take training data, you take test data, and that's called supervised learning, and then you have unsupervised learning where you do not have the answer, right? So in this case, if you had your PCAP files, you're probably not going to know if there's malicious data in your PCAPs. Maybe you do, maybe you don't, but more likely than not, you're not going to know. It's just going to be data that you have in your environment. So if you don't know the answer, and again, the answer in this scenario would be whether or not the traffic is malicious, you would have to use an unsupervised method of machine learning, right? Because you don't have the answer. So if we go from the PCAP to CSV example, there's one little problem with that, and that's that you're not enriching the data at all. And what I mean by that is if you just use plain old PCAP data, you're not going to have things like who is information and all the other stuff that you might want to enrich it with. You're not going to, you know, it might be important feature-wise to know that this IP address comes from China, right? It might be important to know that it comes from Russia. If you're just looking at a plain old PCAP, it's not going to tell you that information without doing some form of enrichment. So here's the OpenSOC kind of infrastructure, if you will. And what this is showing is that you can take your taps, basically transform that into PCAPs, it goes into Kafka, it does all this enrichment at the storm level, and basically it does analytics today. And OpenSOC is also one of the big reasons that we decided to do our current machine learning project. If you look at the original architecture for OpenSOC, you'll see this big OpenSOC ML part of the workflow. So Cisco decided to rip out the machine learning part when they released OpenSOC, basically because they said that it was proprietary, it was super important to Cisco's overall long-term plans, they couldn't release it part of the open source project. Which is really unfortunate because, I mean, the analytics piece that OpenSOC does today, it's great and all, but it's kind of missing the whole machine learning part, right? So analytics are great, a lot of places are doing that today, but the machine learning part would look at those analytics, it would look at the data, and then it would say, okay, here's my decision on it, right? And we already established that there's a resource issue in the information security community. So if there's a resource issue, that means you don't have people able to sit there and look at the analytics every single day, which means you're going to miss things, which means that if you have a model that's trained correctly, you could just have the model sit there and look at this data, and then it can spit out and say, hey, incident response team, out of these 50,000 packets that I saw over the last hour, these are the 7 that are anomalous to your specific environment. So not, you know, that helps narrow down the incident response team's job, or the people whose job it is to sit there and look at all these logs and say, okay, great, I have to focus on these 7 things. And then the beauty is as you actually start investigating these anomalies, you should go back and tell the system, okay, this was a real attacker, this was not a real attacker, right? And then it will learn from that. So that's where the learning part of machine learning comes in, is that as you tell it more and more, it gets better over time. So on that topic of it getting better over time, there's this big notion of feature engineering when it comes to data. And basically what this is saying is you need to look at your data, you need to understand what's there, right? Like, what do you have in your data? So if you just have PCAP information, that's great. Well, what's inside the PCAP information, right? I mean, are we looking at a bunch of port 443 traffic? Is it encrypted? Is it not encrypted? What does your organization do? Are you a health care provider? All this is super important. And then after you kind of look at your data, you extract the features, and then your next question would be, well, what else do I need to really make this useful, right? I mean, how do I take my PCAP data, or how do I take what I have and enrich it with geolocation information or who is information, kind of what we were talking about earlier? You would probably want to add that this IP address comes from China or Russia. And then you take that data, you make your model, and then you basically make this thing called a feature importance chart. And a lot of different algorithms support doing this. But basically what it's saying is, out of all your features, here's what are actually important to making a decision. So in our anti-cheat example, we had 140 features when we started. When we did our feature selection, we narrowed it down to these 5 different features. And this is how we eventually ended up getting from 83% accuracy down, or up to 93%, is you just throw out the things that don't really matter. So again, like data enrichment, we've kind of talked about this. There's a whole bunch of things that you can do to make your data better. We've talked about geolocation, who is information. If you're using OpenSock, they do some of this for you already. They will also do CIF and things of that nature. But really, what it comes down to is you have to know your own environment to know how you need to enrich your own data. This is not something that most people can just come to you and say, hey, here's how you can make it better. People can kind of hint you along the way to make it better, but you know, a healthcare provider is much different than a power company, for example. So once you have your data and it's been enriched, and now you're actually finally ready to actually do machine learning. So there's a couple of, I guess, learning styles, if you will. There's supervised and unsupervised. And again, this just means whether or not you have the answer. So unsupervised is really good at clustering and doing anomaly detection. So what that means is if you have, let me jump ahead here. So here's an example of anomaly detection. So this is a machine learning algorithm, and what they do is they have this data. Again, we don't know the answer. We feed it into it, and the white circles are the training set, right? So this is what we gave the model to learn from. The green circles are new observations that we are going to find normal or regular. And then the reds are the abnormal observations. So you can see like a little red line around there, around these two clusters. Anything that's outside of the red line is considered usually an anomaly. So a better example, drilling down into that, a specific algorithm that does this is called one-class support vector machines. So in this example, we have apples, we have different fruits, right? But we're looking at apples or pears. So it can either be an apple or it can be a pear. But what do you do with the Apple logo, right? Because that looks like an apple. But in reality, the machine learning system will tell you, okay, well, the Apple logo is an anomaly because it's not, you know, it looks different to it. So that's kind of an example of real life anomaly detection in work. So some other machine learning algorithms, a lot of people, when you get started, will use decision trees. When we did our anti-cheat, we use a boosted decision tree to decide whether or not someone was cheating. Basically, all that a decision tree does is it makes a bunch of yes or no decisions. There's a lot of talk about artificial neural networks and deep learning and how we're really trying to get more and more to like a human brain, if you will, of thinking or cognitive computing. We're kind of probably at least 3 to 4 years off before we have a true human functioning type of machine learning model. Watson is pretty close, but Watson has a lot of limitations, and IBM would tell you that. And then support vector machines are probably your next thing that if you want to start using machine learning today, you would start with decision trees, and if you go to support vector machines, would be my personal recommendation. So a really cool example of decision trees was the Microsoft Connect project. So if you're familiar with the Connect, you know, you can use hand gestures and you can use movements, and you can basically do different actions by moving your hands or playing games, whatever. So in order for them to train their system of what body parts look like, they decided to use a decision tree. So they used 3 different trees. They had over, I think, like 1 million images, and the end result was over a day of testing this model, they were able to successfully identify what a human arm looked like, what a human finger looked like, and they have the system up and running. The traditional approach would have been someone would have had to sit there and program that whole thing out, and it would have taken forever. So here are some other resources for you guys to use. There's the IDS data sets that are commonly referred to. If you start reading some white papers on machine learning in the Infosec space, they will refer to both of these. The first one is the KDD99 data set. This has been enriched. Both of these have actually been enriched, and what I mean by that is if you look at the data sets, they have the classification of what that IDS data is. So it'll actually say if it's like a buffer overflow, it'll say if it's, I don't know, just in-map scanning, they have regular port scanning, but they tell you the answer, right? And that goes back to the whole notion of supervised versus unsupervised. You can use these in a supervised machine learning algorithm. The other one is the NSL KDD, which is just a more enhanced version. Some people found some issues with the KDD99, and the NSL KDD was the result of them pointing out those issues. So the closing stuff I wanted to talk about was the current market of machine learning today. So I recently went to Black Hat this year, and I spent quite a bit of time talking to all the vendors that were there. And a lot of them were making claims that they started to use machine learning in their products, and that's what made them different than everyone else. So my question to a lot of those vendors was, okay, well, you guys are using machine learning. That's great. I mean, what kind of algorithm are you using? What kind of results are you seeing? You know, how accurate are you? And I kid you not one single vendor would answer any of those questions. All of them said, no, that's proprietary information. We can never tell you that. You know, that's secret sauce. That's, you know, looking under the hood. But the reality of that situation is that it's not secret sauce. I mean, that's how you would evaluate whether or not this stuff is working. So I like to kind of equate that to, you wouldn't go out and buy a car today without looking at the car sticker of, hey, here's the mile per gallon, here's what the horsepower are. I mean, maybe you would buy the car without seeing that information, but again, these are like kind of the common metrics in that industry. So the ML sticker, the machine learning sticker, so to speak, you should be asking things from vendors that are making these claims. Well, what are your, what is the accuracy? What is the precision of your models? Do you guys have a rock curve? So that image over there is a rock curve. And the more that looks like a upside down letter L, the better that it's performing. So as you can, I don't know if you can see the colors very well, but excellent is yellow, good is pink, and pretty much worthless is the purple line. But again, vendors should be proud of this. I mean, if you're really using machine learning, and it's what actually makes your system better than some of your competitors, they should be showing you this. They should say, look at how great our product is. Look at, here's our accuracy. Or sometimes if they don't show a rock curve, it's okay if they tell you what the mean absolute error is. That's another common metric. But after you get over the performance questions, the next questions that you should ask revolve around scalability. So machine learning has been kind of gaining popularity in the supply chain. And what I've been telling people in that industry is, well, ask them, if you add a new store, can you just plop that in there? Same thing in Infosec. If you guys add a new department, or if you add a new firewall, is their system going to be able to integrate with your new firewall, right? And I understand that might be a hard question for them to answer because they don't know what you're going to, but they should at least say things like, well, if they have an API that we can access, sure, we can start pulling in that data. And then the final thing to ask is, well, what about new features? So feature selection is super important, and as your organization grows and as you learn more and more about your data, you're going to want to add more features. You're going to want to make your models better. Ask, is that a hard process? Is that something that you can just, do if you had a new idea? Or is that going to be a whole new development process? So here are some additional resources. Weka is an open source project. It's Java based. You can download it today. It has a whole bunch of different algorithms in it. You just load your data into it and you can start messing around with it. There's a couple of additional data set resources here. Kaggle is a very popular machine learning forum and board. You can go out there. There's these competitions where companies like Walmart and Caterpillar put their data out there and they say, hey, here's our problem. Here's the data. Just use machine learning and figure out how to do it. And then they score you based on how your model performs and if it answers the question. So it's kind of cool. I mean, you're competing against a bunch of other people. And then the final link down there is about HDP, and I just kind of mentioned that one because, again, you can go there, you can download a sandbox environment that's a virtual image. You don't have to do a lot of configuration, just get up and going. And the specific link there is about visualizing server data logs. So I thought that might be relevant to some people. But really, I think the main takeaway with all the noise that's been going around with machine learning lately is machine learning is really a tool, right? It's a tool to help organizations start making better data-driven decisions. And this has been an initiative for a lot of C-level executives is we need to get away from making gut-based decisions. We need to make our decisions based on what the data is telling us. And machine learning is, again, just one tool in the arsenal that people should start using. It's never going to be, well, I shouldn't say that. It's probably never going to be, in the next 10 years, something where you can just implement and it's going to sit there and take care of all your security problems. It's just not going to do that. Again, it's something that you can use in your processes today to help reduce the work, but you cannot just think that anyone's ever going to create something and say, well, we use machine learning so you're secure. That's not how it works. I know, I'm sorry to burst some bubbles, but so here's my contact info. I put Jason's contact info up there as well. Jason actually leads our data science team, so I apologize for some of the lack of depth, if you will, on certain topics today, but again, he is not able to be here. So I will open it up to question and answers if anyone has any questions. You, sir, there in the back. Yeah. Sorry. I thought that I could drink water, but apparently no. All right. Sorry about that. So one of the cool things that they're starting to do is SQL injection. SQL injection has been something that we've been struggling with ever since SQL has been invented. So what they're starting to do is take training sets of here's what a SQL injection attack looks like. And they're training the models and they're saying, going forward, can you classify whether or not this is a SQL injection attack or if this is a very legitimate use case? I think as we evolve, you're going to see more targeted machine learning examples. So trying to say that it's just going to do Infosec, that's not going to be the solution. It's going to be very targeted stuff, like we will identify SQL injection with machine learning, or we will identify malicious files, binary files, things like that. So what's your question? Or, oh, okay. Well, sure. So, yeah, the real-time stuff is important, but that's not necessarily a domain of machine learning, right? that's an infrastructure problem. So Spark is an example of how they're solving that issue. Spark will do real-time data processing. And once the data is processed, then yeah, the machine learning can start doing it. To a certain extent, yeah, it's about how fast can the machine learning look at that new data. But the real problem is from an infrastructure standpoint of how do you do real-time data processing, right? Any other questions? Yep. Right. So the way and the maturity of where things are today, you would never just want to put machine learning into place and say, okay, if this thing identifies it as SQL injection, shut down the IP address, right? You still need to have a human level of due diligence, if you will. Look at the results that the machine learning system is spitting out, and then have them make a decision as to whether or not they believe it. So today I think we're at the point with ML where we can take it and we can look at data sets and we can say, okay, hey, look, you know, there's this anomaly over here. Analyst 1, you need to go investigate that anomaly and see, you know, what this thing is, and then come back and tell us the results, and then kind of go from there. But no, today I don't think that we are anywhere close to the point of saying like, hey, look, we have the solution, it's going to find it, it's, you know, 99.99% accurate. If it says that it's malicious, let's go ahead and shut down the IP address. We're not there yet. Yeah. So the question is, how much time do I think that this can reduce for an analyst? I think that you could take years worth of work and probably reduce it to a couple weeks. I mean, it would also be an efficiency thing as well, right? It's an interesting question in the sense that it all depends of what your analysts come back with, right? So if you build your model and they're looking at the anomalies and they're investigating those anomalies and they're saying, okay, this was a real event, right? And it might not be an attacker, but it might just be like, you know, some executed or program got executed on the box and it wasn't supposed to do that. Sure, you know, why did that happen? But as they get more familiar with it and as they are reporting their results, it just feeds into the whole cycle, if you will, right? So as time goes on, yeah, more and more work will get reduced. They'll trust the results more and more. The model gets better. Like everything will just have an impact on helping save time, efficiency, all that stuff. Yeah. So I think, right. Well, I think like today, the honest use case for this is, you know, I've been at these organizations where you don't have people look at the data every day. You don't probably have people look at the data, but maybe once a month because they're tasked with so much other stuff. No one has time to sit there and look at this dashboard and say, okay, yeah, here's my sim dashboard. Great, that thing's red. It's been red for the last 3 years. Who cares, right? Like, but I mean, that's the reality of the situation. I think immediately if you start using machine learning, yeah, it might not be super accurate, but at least something's looking at it, right? At least it's being at the lowest level of due diligence possible beyond nothing, right? So, and I think that your analysts will start actually appreciating, okay, this machine learning thing is great because it's actually able to look at all this sim data or whatever data you have and say, you know, it reduced that to these 7 or 15 or even 30 anomalies where I can go and spend 10, 15 minutes and determine that this is a real attack or not, right? So I think that's kind of where we're at today. And then long term, yeah, we'll be at a point where we're actually able to detect a breach in a matter of, hours or days even, you know, better than the 200 plus days that we're currently at. Anyone else? I don't bite, I promise. All right, well, thanks for coming and listening to me talk. Have a good DerbyCon.